Hi, and welcome back to Allen High School's discussion of reactions at the pre-AP or 10th grade honors level. We're predicting reactions, and at this point we're going to move into single replacement, sometimes called single displacement reactions. Now, what's nice about these in terms of our discussion of whether they are redox is that these are always a redox. So you can go through those boxes and tick them all off as redox because we're always taking an element and putting it into a compound or pulling an element out of a compound. You can think of this, Ms. Marusik does, let's dump and get a new boyfriend or girlfriend, kick the other to the curb. In my little world of analogies of all attractive and repulsive forces, this would be me, this would be my husband, this would be, of course, Denzel Washington. And what's going to happen is the attractive force between Denzel Washington and myself would be such that we would start dancing together, and he would cut in, and my poor husband would have to sit on the sideline for a while. Not too long, though, because my husband knows that deep down I love him more than anything. So, and yes, he is aware of my obsession with Denzel Washington. Now, let's take a look at how we're going to do this. Now, bear in mind that the substances that we're going to talk about are going to be changing oxidation numbers, and we have to make sure that we pair up the correct oxidation numbers. We don't put negatives with negatives. So I have a solid piece of zinc. Now, a solid piece of zinc all by itself is 0. And we're going to add that to a solution of silver nitrate. So we would have AQ. Now, these will bond according to their charge rules. Now, silver is +1, nitrate is -1. Now, zinc wants to become zinc +2. So zinc +2 wants to dance with the negative nitrate, not the silver. So I would get silver nitrate. We can take care of the fact that there's 2 of those later on, okay, in balancing. And that leaves poor silver all by itself. And I'll tell you, one of the biggest mistakes is people will leave silver as a charge. Silver is going to go to 0. We're not going to deal with ions remaining as ions. It happens, but we won't be dealing with them at this level. So in single replacement, make sure you have an element with a 0 oxidation on one side and on the reactants and one on the products. Now we have to account for the fact that they bond differently. And I have 2 nitrates on this side, so I need 2 there. That means I now have 2 silvers. So I have to put a 2 in front of the silver. And I'm hoping by this point of the unit that you've wrapped your mind firmly around how to balance a chemical reaction. Right, because I'm not going to go through the details in a video. I will gladly go over more details in class or during a tutorial if you need that extra little boost of help there. Okay, lithium. Lithium's a metal all by itself. It's lithium solid with a 0 oxidation or charge, plus barium hydroxide. So it helps, I think, to put the charges underneath like that. Okay, now, when lithium goes into a compound, it's group 1, so it wants to become +1. So now you have to ask, is it going to dance with positive barium or negative hydroxide? And we don't do positives to positives in chemistry. There's just no attractive force there. So we're going to put lithium with hydroxide, and that leaves barium all by itself. Metals are solids, okay? And I do need to balance it. I forgot one state here, that's aqueous. We're going to talk about solubility rules, and we're going to see that that's aqueous as well. So we'll get into that later. Okay? Fluorine gas, F2, not Fl, just F2, is bubbled through strontium bromide, and that's aqueous. Okay? Now, fluorine 0, strontium's +2, bromide's -1. Now, here's a little bit of a difference. This is kind of like, I don't know who my husband would think is beautiful, but here's my husband, here's my husband, and maybe this is, I don't know, Angelina Jolie or somebody like that who's like really gorgeous. And of course, negatives are going to trade places here. No, I guess I did that analogy wrong here. Okay, but you get the idea. Okay, strontium is going to go with fluorine because strontium's positive and fluoride wants to be -1. That leaves bromine all by itself, but be careful because bromine all by itself is a diatomic. Now, you don't have to know this solubility rule, so we would give you a hint on that that's a solid. And remember, all single replacement are redox. Okay? Magnesium, this is a slightly trickier one. Magnesium is added to phosphoric acid. Do you see how quickly you have to be able to write chemical formulas now? All right, here's tricky, but again, if you're careful about writing charges underneath, I think you'll be okay. Remember, phosphate's -3, the protons are +1. Now, when magnesium goes into a compound, magnesium wants to be +2. So that means it's got to react with the negative. So we're going to have magnesium phosphate. Now, hydrogen is all by itself, but remember, hydrogen's never all by itself because it's a diatomic, and it went to the gaseous state. And yes, this is a redox. This one's slightly trickier to balance. I've got 2 phosphates on this side, so I'm going to put a 2 there. 3 magnesiums, I'm going to put a 3 here, and that's going to leave me, I think, with 3 hydrogen gas. So let me know if I've made a mistake there. All right, sodium is added to water. Now, in a single replacement, I strongly recommend that you write water as HOH, or you're likely to make a mistake. I see it every year, about 30% of you, and I would like to see that get down to, let's say 0% of you doing this. You can think of water as being made of the +1 proton and the negative hydroxide. If you don't write it this way, there's a tendency to write the product as Na2O, and that's not what happens. Do you see, if you write water that way, it kind of implies that. But if we write water this way, hopefully you see that the sodium's going to go with the hydroxide, and that leaves hydrogen all by itself. Gas, aqueous, pure liquid. Okay? And we do have to balance that. I need a 2 here, a 2 here, and a 2 there. And that's balanced, and it is a redox. Okay? So the key when you're doing single replacement and water's involved is to write water as HOH. You want to avoid that pitfall of forming an oxide. You want to form an hydroxide. Okay, so let's see. We've got one more here, and then we will head on to double replacement. Whoops. We've got, notice it gives us the products this time. This is just a nuanced way of doing it, just not more of a flipped way. All right, so magnesium chloride and hydrogen gas. So it's the same process, right? If hydrogen's all by itself, hydrogen wants to become +1. The chloride is -1. So that means that the hydrogen wants to go with the chloride. Must have come from hydrochloric acid. So if we drop magnesium into hydrochloric acid, which we will, okay, we will see hydrogen gas bubble off. And again, yes, this is a redox. All single replacement are redox. Magnesium went from 0 to +2, meaning it lost 2 electrons. The hydrogen, and in fact 2 of them, went from +1 to 0. So they gained 1 electron each. Okay? All right. See you soon, kiddos. Love ya.